My name is Andrzej and I'm working for Effitest Systems, a company which produces and designs testers. Today I would like to show you Effitest E-Series, in particular Effitest E50, which is a tester designed for testing small signal discrete components such as diodes, transistors, LEDs, photodiodes and so on. The Effitest test system consists of three pieces. First is test head, second is power box, and the third is IPC industrial computer. Power box serves as a power supply for the test head and for the IPC. It could be attached to a rack separately or directly on the handler, but the main core is in the test head. Test head has two test units. One is, we call it CVI, one is fully capable of testing one test position on the handler. One CVI consists of two VIs, voltage current sources, capable of forcing and measuring 30 volts and 3 amps each. One high voltage source, 600 volts, and leakage current meter. All sources have digitizers, so you can display in the software the waveforms of the power supplies and the measurement itself. One CVI can test one test position on the handler, and in this today I have two CVIs here, the model called Effitest E50 Dual, which is capable of testing in a serial or parallel mode. This means that you can connect the one CVI, each CVI to one test position, test position number one or test position number two, and you can either test the same component, half of them on position 1 and half, and the other half on position 2, or you can test two devices simultaneously in a parallel mode. Connecting the DUT is simply with this cable. You can connect the cable here to the output of the CVI. This is a 3-pin configuration. It could be further extended by external multiplexer, which has another 10 pins. So in total you have 10 pins, and you can switch between more pins and test more pin component. But this configuration has 3 pins. This side of the cable goes either on the handler position or, like I have here today, manual adapter for testing manual components such as transistor here, which is 1815 Toshiba transistor. On the back side of the test head there is a handler interface which is powered by this connector which goes to the power box. Communication with PC via this cable, signal cable, and to handler it's connected by Centronics 50 cable, this one, which could be further adjusted if necessary, if there is a different type of handler, not standard one. These signals are standard IOs, programmable 32 pins. Of course it could be further adjusted if necessary, if the handler is again not a standardized handler. Our testers are controlled by our own software called Skedus. Skedus has two modes. One is for production, which is for the operators, and the second is for engineers, called Engineer. Right now and today I will be showing you just the engineering mode, because in production mode there is actually nothing to set. You can only monitor the parameters, the statistics, test times, counters, and so on. Today I will show you how to program a simple test for transistor. I have here a 2SC1815 transistor, and also what are the options in the engineering mode which are possible to set. If I choose the engineering mode, I'm in here, and the main menu is like this. only enabled button is actually a load button, so I will load a pre-made test, which is this 2SC1815, and test that is still powered off, so I need to switch it on. I can do it either by button on the test head, or sorry, in the power box, or by software button here. So let's turn it on. The power up is detected automatically, so I know that it's green, the test head is powered on, and I can start testing. This is just a simple test of a transistor, basically all DC parameters which are stated in the data sheet. If I go to Edit Test, I can change the configuration of the test head. Here this is one CVI configuration, so one CVI directly goes to one test position in the handler. If I would like to have two tests, parallel or serial, I would choose here the two side counts, which means two CVIs. Test program count means either serial or parallel. Multi-sign means parallel. Carousel means serial test. Pin switch option is if you want to change the pin out of the test position, base, collector, emitter, or similarly on MOSFET, gate, source and drain. I don't need to do it here because it's fixed position and it's right position, so I will not do that, but it's configurable. Here this option is for external multiplexer, as I mentioned earlier. If it's needed and you need two more pins than just 3, you can extend it by external multiplexer to have 10 pins, and then you need to configure it also here. Stop at fail feature enables and disables stop at fail, so when there is a fail in one test step in all test program, it instantly stops. This is as precaution for not damaging the component if there is a serious fail. You can turn it off or on. Then there's another option called oscilloscope. You can turn it on if you want to see the waveforms. This is from the captured by the internal digitizers inside the CVI. And then of course binning. So if you want to set pins, hardware bins, software bins, sorting for pass fail, for different HFEs, for different intensity if you are checking LED, and so on and so on. Right now I will leave it to just one side, one test position to keep it simple, and then I will move to another tab which is called program. I can see my test program here. This is actually test program constructed from the datasheet. As you can see, the first 3 test steps are just checking the Kelvin measurement. It's checking if there is a component or not. If the component is present in the test socket or in the test position. Other test steps are VBE, VBC, breakdowns, currents, saturation voltages, and gain HFE. So right now this is my test steps, and I can easily modify them in the property inspector. If I want to change this parameter, I will go here for the parameters. Polarity is given by the component itself, so I can check if I can change it from NPN to PNP. Set up the current. Here this is the current which goes into collector. VCE, which is voltage across collector and emitter. Limitation of base current, limitation of VBE, base emitter voltage, and force time, how long I want to have the pulse, which is going to the component, and actually this is the capture period. The shortest time is 10 microseconds. I can fully extend it to 100 microseconds, and then the samples are averaged through the whole window, through the whole measurement window. Again, pin switch, I can check switch the polarity if necessary for the given test step. Stop at fail feature, and lower limit activity, upper limit. Here I'm setting the result limits, so lower limit, true fail, and upper limit, true fail. Display unit format, as standard we are using 3 decimal points. Let me close the program and check it again. Switch it on. Again, pass. The problem here is that I can see only the last run of the test system, so the last results. To have more information about the testing, we are using so-called data log, which is automatically launched in the production mode. So if the operator is operating the tester, or if it's on automatic mode, the data log is always there. And locally, we are storing all the measurement data. So if I put there data log, the name of the data log, they are stored in C schedules data log. I can define log rate, which can be each test run, or every second, every third, whatever is there needed. I can limit it if I just want to record few, like 100 first runs, but I can, if I have 0, it's infinite, so it will be always stored. Choose the test steps which will be recorded, and also I can extend it by the operator name, and I can put there a custom device number. So right now I will open the data log. Looks like this. Let me do 50 runs, continuous runs, so I have some data here. Right now it's filled with data. I have here the overview of data. The Data Log Explorer uses SDLG format, which is our own format, but we can export it to Excel file, CSV, standard data format, or PDF. Here is the summary of our recorded log, counters, which devices were fail, not fail, and which test steps failed and how many times. Variables, this is just a set of variables. It's not really important for the engineer. Statistics, this is really interesting feature that you have automatically calculated the CPK, CGM, standard deviation, average, minimum, maximum, and all the statistics needed for the post-processing of the data. And another very interesting feature is the histograms and trends. You can see the parameter, how it's evolving during the time, during the measurement. So for some parameters, you can see how the component is heating up. So this blue line, which is the result, goes up and touching nearly the upper limit, or how it's actually jumping, or it's not stable during the time. This is similarly like on here, and you can see here. So this is data logging, and another feature I would like to show you is actually the virtual scope. So when I'm writing the test and I really want to optimize the test time, I want to keep it as short as possible. So I can take each test step, turn on the oscilloscope here, and then check the waveform. Here I have all the sources, internal sources, which are digitized. The first is called VIV, so I can see the voltage on VIV, and current on VIB. The second source is called VIC. It stands for collector, C, B stands for base, but as I mentioned earlier, this could be switched other vice versa. It's configurable. It's just a name here. It can be the same as power supply number 1, power supply number 2. This is the voltage across voltage VIC, current VIC, current voltage on high voltage source. As you can see, here is nothing. It's just some red noise because it's not used in this test step. And leakage current meter, which is also not used in this test step. So when I'm setting the test, VBE is just a simple junction, so I'm expecting value between 0.7 and 1 volt, and I can see immediately that here is this is my desired value, and it's stable after 200 microseconds. Let's say I can measure it with cursors. So here I have the desired value. So after actually 100 microseconds here, I can consider this value as stable. So if I need to optimize the test, I will go back to the VBE, and first times I can shorten it to 200 microseconds. Right now, you can see that I shortened the test time by 100 microseconds, and it's still stable. I can use it on and on to keep it really optimized. Without digitizers, I couldn't know where is the value stable. So this is really interesting and a very helpful option which we have. All Effitest have this feature, internal digitizers. Let me tell you more about other options which we have here. First, out of the 3 modes which we can run, it's either manual, which is one run, automatic. This is with the handler. So when the handler is connected, it's waiting for the start of test signal, and then for the end of test signal, and of course it can have another signals. And loop is that I'm actually making the testing on the same device, like let's say 100 times, 1,000 times. So this is one DUT constantly testing, retested again and again and again. I can display other from the test properties and test results. Also the counters here, so I know how many fails I have, how many passes I have. Test times, this is also important for optimizing the test. So you can display how much time takes to test one test step. And if I need to optimize something like ICBO here, I can focus on the longest test times and see on the virtual oscilloscope if it makes sense to shorten the test time or not. And test conditions, this is used when you want to export automatically the test specification of the given component. You don't need to fill any external form, this is automatic again. What I also would like to mention on the end is that we are providing really detailed help guide. So in order to debug tests properly, you of course know what you are doing, because what sources are switched on and off. Because if I want to check, let's say, it's tested like VBE, this is some principle here. I have this test method which is very well described, and you can see the DUT here displayed, how is connected the high voltage source. Sorry, this is the VIC source, high side, low side. This is the VIV source, it's in current mode, and leakage measurement is here on the base. So all is well described, all the methods, every method. You have also here the ranges which you can set, and with this you will always know how to program the test and what should be the expected result. So this is basically it. This quick overview of the capabilities of the system. So thank you for your attention, and let me know if you have any questions.